I've got a question for you. Who of you is able to draw a dog? Raise your hand. Okay, there's some plenty of people. And that's typically how people draw dogs. So we start with an outline of the dog. Later on we add more details. You add the face of the dog, ears, also the legs. We add more and more details. We add some shadows and fine-grained details. And that's very similar how diffusion models draw dogs. They start from a pure noise that has no information in it, and slowly remove more and more noise from it. And similarly, we start with an outline of an object, and later on, we add more and more details until we end up with the final picture. Today I will talk about why diffusion models are important, how do they work, and how to make them faster. Let me start with introducing some of the hardware that all of this can be trained on. There are some solutions from HPE that allow for generative AI training, fine-tuning, as well as inference. There's a software stack from NVIDIA, as well as switches, networking, and some chips that we can use to train these models. Most notably, H100 and Grace Hopper chips. They're all packed in HPE server solutions that can deliver your generative AI capabilities to you. All of this can be packed into one server solution for you. It can leverage NVIDIA Rapids. It's an open source library that can speed up your data processing pipelines by an order of magnitude. And there is also NVIDIA Triton server combined with the NVIDIA TensorRT that can help you deploy your models. All of this is really nicely packed for different use cases, for AI at the edge, also for visual apps, 3D animation, image or video applications, as well as LLMs, speech recognition, as well as fraud detection. And these solutions can handle up to 4 H100 chips. And all of this hardware is very important to leverage these models. But why are they important? On the left, you can see NVIDIA Edify. That's a text-to-image model. So given a text prompt, it can generate high-resolution, high-quality image. And specifically, this model is very, very good with generating humans. On the right-hand side, you can see NVIDIA Edify 3D. It can be used to generate 3D assets, for example, for game development. And other modalities can be used with diffusion models as well. Here is an example of OpenAI Sora. That's a text-to-video model. And that's quite remarkable that given a very complicated text prompt, we are able to generate up to minute-long videos that really nicely represent these prompts. But not only that. Diffusion models can be also used for drug development. For example, RF diffusion model is able to generate protein structures that can be later used when developing new drugs. And quite remarkable, we can also use them for weather prediction. NVIDIA CoreDiff model is able to upsample low-resolution predictions into higher resolutions. And it is very, very important. For example, when a typhoon can hit Taiwan, it is very important to have very precise predictions, and that will help us to mitigate the damages. Another technique that is very popular right now is 3D Gaussian splatting. The idea is, what you can see there is not real. That's a scene that is 3D generated. And we can move around with a camera, and we are able to generate new views from this very complicated scene, basically in real time and in high quality. diffusion models can change a lot of industries. Autonomous vehicles, product design, visualization, and many, many more. And let me show you a short clip coming from NVIDIA GTC conference this year that can illustrate how diffusion models and the generative AI can change our world.
这款车型焕发出独特的魅力。
我喜欢有质感些的灰色。
非常好的选择。
So we know what we can do with them, but how do they work? Let me start with latent space. VAE, Variational Autoencoder, allow us to translate highly dimensional data into a lower dimensionality space. So let's say that the original sample, called X here, is just a picture in a pixel space. We can use an encoder to encode it into the latent space that has lower dimensionality. So it's easier to work on this data. And later on, we can also use a decoder architecture to decode it back to the original space. So basically, when we start with an image, we can later on encode it and decode it to obtain X prime, which should be very similar to the original image. And it does not really have to be an image. It can be basically anything. It can be video, it can be speech spectrogram, whatever. Another very important concept that will be later on important are GANs, generative adversarial networks. Here we have a generator network and a discriminator network. The generator generates synthetic samples, and the discriminator needs to discriminate between real data coming from our dataset and the synthetic samples generated by the generator. Both of these approaches can be used to generate new samples. A third possible approach are flow-based methods. Here, we need to learn a flow function that would translate our data into a Gaussian distribution in the latent space, and later we can reverse this process to generate the data from the latent space. And there are diffusion models. They work completely different. In diffusion models, we start with an image, and what we can always do is to add more noise to the image. That's pretty straightforward. But when we are adding more and more noise, we finally end up with an image that is pure noise, that has no information in it whatsoever. The tricky part is to reverse this process. We do not like to add noise to the image, but we would like to remove noise from the image. And that's how we generate our samples. we start from pure noise, and we gradually remove more and more noise using neural network until we end up with the final image. Why are they so different from other methods, and why they are so popular right now? The thing is, they are, first of all, they produce really high quality samples. The images that they generate are top-notch. Also, the problem with previous approaches, such as GANs, was that the images wasn't really diverse. So when you ask a GAN to generate an image of a cat, like 10 times, it would generate 10 very, very similar cats. When you ask diffusion models to generate 10 pictures of a cat, they are all different. So what's the catch? They are much better, but there is one very important downside of the diffusion models. They are painfully slow. They can require up to 100 more neural evaluations than GANs. So that's pretty painful. And for some cases, that's just too long. For some use cases, we can't wait for a few seconds to generate the image. Later on, I will talk about the optimizations because of the slow generation speed. And right now, there is a timeline of a few diffusion models that were created by Stability AI. There is Stable Diffusion XL, and Stable Diffusion 3. These three models have been trained from scratch. And there are two additional models called SDXL Turbo and SD3 Turbo. They have not been trained from scratch. So we start from the SDXL model, and we only fine-tune it to obtain SDXL Turbo. Similarly, we start from SD3 model, and we only fine-tune it to obtain SD3 Turbo. What's this turbo meaning? Well, what's this fine-tuning technique? I will talk about it later. And now let me just quickly introduce you to how Stable Diffusion works. In Stable Diffusion, we start from the pixel space. The X represents data coming from our training dataset. We use our pre-trained encoder to encode it into the latent space. And here we perform a forward diffusion process. That's a pretty complicated name. So forward diffusion process meaning we just add noise to the image. We can always add noise to the image. That's pretty simple. The tricky part is to reverse this process. So here we have an image in latent space that has a lot of noise in it, and we ask our neural network to remove it. We added this noise so we know what the neural network should predict, and that's how we train it. We also can condition on different things. Most popular choice is to condition on text. So let's say that given a text prompt, we ask our model to generate an image that corresponds to the prompt. We use a standard unit architecture. There are some cross-attention blocks that allow us to pay attention to the conditioning, and that's how this model knows to pay attention to the text that we provided. Our neural net removes the noise. We calculate MSE, mean square error, between the predicted noise and the actual noise, and that's how we train it. When it comes to inference, we start from a pure noise. So at the beginning, we have an image that contains nothing in it, just pure noise, no information whatsoever. And we run this model multiple times. We can remove a little bit of noise and use it again and again and again. And in the final stages, we just end up with the final image that has absolutely no noise in it. We also need to decode it back to the original pixel space. And this is our final sample, and that's how images are generated. SDXL is a very similar architecture. It's 3 times more. It has 3 times more parameters than the previous one. It produces better quality results, and it also adds a refinement model. That's like an additional neural net that is specifically very good at enhancing the very fine-grained details in the final image. So basically, our base model generates an image, and later on, we only a little bit improve it by our refinement model. And also, it was trained on multiple aspect ratios. Here on the right, you can see some of the images generated by this model. This model is pretty fresh. It comes from February this year, 4 months ago, and Stable Diffusion 3 has an amazing typography. Here you can see on the images on the left that the text present on the images is very nice quality. The model performs really well with the text description and can generate those descriptions on the image. It was trained slightly different. It was trained using flow matching. It's a little bit more general approach. It's very similar to how we originally trained diffusion models. And it was based on a transformer architecture. So previously, we have used units with convolution layers, but now the community slightly shifts towards transformers. As you might know, transformers are a very popular architecture in LLMs. They are used to process text, and that's very interesting that these ideas are coming through different domains. And right now, the diffusion models work very similarly as transformers in NLP. I mentioned before the main problem is their long generation time. There are a lot of optimizations that we can use. And basically, there are 2 types of optimizations. First of all, we can optimize the backbone itself. So each of the diffusion steps can be faster. There are methods like pruning, quantization, or model compression. On the other hand, there are sampling optimizations. So I mentioned before that diffusion model needs to perform a lot of diffusion steps to generate the final image, and we would like to make them more efficient so that we would require fewer of these steps. One very interesting approach is distillation. Distillation is a technique that allows us to transfer the knowledge from a teacher model to a student model. We have collaborated with University of Warsaw, and some students, as a part of their bachelor thesis, worked on progressive distillation. They have worked on a model for speech generation. So that's a model that starts from a pure noise, but unlike previously, we do not generate an image, but we generate a speech spectrogram. It's still a diffusion model. It needs to perform several steps. And what we can do is to distill subsequent diffusion steps into a single one. So these 2 steps can be merged together, and we have half as many diffusion steps. What's very interesting, we can repeat this process. So we can distill it once, and we can distill it once again. So again, we distill these 2 subsequent diffusion steps into a single one. And this process can be repeated multiple times. When they have started, this model required around 1,000 diffusion steps. And after the optimizations, it was an order of magnitude faster. I would like to tell you how we evaluate these models, because that's a tricky part. So the approach is we can ask humans what do they prefer. So there are 2 images coming from 2 different models. the participants usually don't know which one is which. So they don't really know, they're not biased towards any specific model. And basically we ask them two questions. The first one, which image is more aesthetically pleasing? So which image has better quality? The second question is about alignment with the prompt. So we ask them which of these two images aligns better with the prompt. So here we have a prompt, a cute corgi dog lives in a house made of sushi. And we can see that both images are pretty nice quality, but there's a problem with this one. So the dog is not really inside of the house made of sushi. So the image on the right corresponds better to the prompt. And now, finally, I would like to talk about SDXL Turbo. What this turbo means. It's an adversarial distillation. That's a very powerful technique that can speed up your model of around an order of magnitude. It can be around 10 times faster. So previously, SDXL required around 50 diffusion steps. We had to use our model 50 times to perform 50 diffusion steps to generate the final image. But this model is much faster. It requires only a single diffusion step. All of these images have been generated using a single diffusion step. All of them have been generated under 1 second. And the quality is pretty good. So on the right-hand side, you can see the evaluation results. These are evaluations coming from the image quality question. And the longer the red bar, the more preferred this model is. On the left-hand side, you have SDXL Turbo. On the right-hand side, you have a bunch of different models from the literature. And as you can see, SDXL Turbo, with only 4 diffusion steps, outperforms all of the other models. And there is one very interesting fact that our fine-tuned model with 4 diffusion steps is better than our baseline model with 50 steps. So basically we went from 50 diffusion steps to just 4, and we have a better quality. So how does it work? We start with an image coming from our training dataset. We use a pre-trained encoder to encode it into the latent space. We add some noise to this image, and we ask our student model to denoise the image. The student shares the architecture of the teacher. So we are using exactly the same architecture, and we also initialize student with the weights coming from the teacher. After that, we use a pre-trained decoder to decode it back to the pixel space. And now the training begins. So here we are using a distillation loss. This procedure is repeated for the teacher model. So this image is now encoded back to the latent space. We add noise to this image, and later on we use our pre-trained teacher to remove the noise from it. So this part is very similar. The only difference is that here we are using our student, and here we use our frozen teacher. The teacher is not being trained here. We are only fine-tuning our student model. And after we decode the output of the teacher, we basically compare these two images. Here we are calculating MSE, mean square error loss, to calculate the distillation loss. There is one more very important factor in here. The technique is called adversarial distillation. So we are using a discriminator coming from a gun. we are using Dyno-V2. That's a feature extractor network that was developed by Meta. Basically, it just takes an image as an input, and it outputs a set of features that allow us to understand the image. These are the features that tell us what's inside of the image and have some very important information that can be later on used by our discriminator heads. So the backbone of the discriminator is not being trained, only the discriminator heads. The discriminator heads are very lightweight and have very few parameters, so they are easy to train. That's pretty remarkable that we can obtain such an amazing speed up with this technique. And it was later on even improved in SD3 Turbo. On the right, you can see the images coming from this newer model that was developed 4 months ago. And on the left, you can see the results of the evaluation. You can read it very similarly as previously. So participants were asked which image do they prefer. On the left-hand side, you can see SD3 Turbo. On the right-hand side, you can see other available diffusion models. The longer the red bar, the more preferred SD3 Turbo is. And it outperforms almost every model. And once again, SD3 Turbo model produces on par results with the baseline model. So once again, we are distilling this model that needs to use like 50 diffusion steps into 4 inference step diffusion model. I will talk about how this new improved version works. So here is ADD, that's what I previously talked about, adversarial diffusion distillation. And here, this new technique is called LADD, latent adversarial diffusion distillation. It's a simplified version of the previous approach. We start with a pure noise, and we use a pre-trained teacher model to generate the synthetic dataset. So here, we are not using any real data for the training. Everything that the student sees is generated by other diffusion model. So we are in an era of AI that the models that we use are not even trained on real data, but our models are trained on data that was already generated. The teacher only sees the prompts coming from the dataset, and using this prompt, it generates the latent representation of the images. This whole first step can be pre-computed, and during the second phase, we start our actual training. We add some noise to these synthetic images and ask our student model to remove the noise from the image. After that, we use, once again, a discriminator that will discriminate between images generated by the student and images generated by the teacher. The images coming from the teacher, we call them real images, and images coming from the student, we will label them as false. So I am talking about generating images because it is the simplest case, but you can think of any different modality. Whether it be images, videos, 3D objects, whatever, it doesn't really matter. This technique will handle it all. So, why is it simpler? First of all, the previous technique required 2 rows to represent it, and this one only 1, so it's pretty short. And there are 3 main differences. The first one is the discriminator. So previously, we had to use a third-party network. Here, we are reusing our teacher model. The teacher model acts as our backbone model, and once again, we just only add some lightweight discriminator heads. Again, they are pretty small, they have few parameters, so the whole technique is very easy to train. The whole fine-tuning process takes under 1% of total time required to train this model. So if we wanted to train such models from scratch, we would need a cluster of hundreds of GPUs working for a few weeks. But this whole fine-tuning technique will allow us to generate such models in basically a few hours. The generator is producing adversarial loss, but there is no distillation loss, so there's only one loss factor. The second important difference is everything happens in the latent space. So previously, we needed to juggle between pixel space and the latent space, and we had to use our encoder and decoder networks. That was pretty troublesome because the gradients had to flow through all of them, and we had to have like a lot of components in the GPU memory. That was a little bit troublesome. The whole procedure is much simpler now. There are fewer components. We only require the pre-trained teacher model. It's pretty fast, and the results are very nice. Throughout the talk, I mentioned a lot of generative AI models, and a lot of them are available to you using NIMs. NIMs are NVIDIA Inference Microservices. They are production-ready microservices available via an API. So basically, you can just drop them into your production application. These models are accelerated by NVIDIA, and also some of them are available via browser. So I'll give you a couple of seconds so you can scan the QR code and play with the models that I have just talked about in your browser on your phone.
And probably you can think about the questions as well, because we're approaching the end of the talk. Thank you.
Yeah. Another, and NVIDIA has been very generous and is sharing with you coupons for Deep Learning Institute. They are worth about up to $90, and you can get started with some courses about deep learning, accelerated computing, also with computer vision and speech recognition systems. You can scan the QR code to claim your code, and you can later on try these courses. Okay, and that's my final slide. I would like to thank my team for making this work possible, and thank you for your attention.
Thank you very much. That was a great talk. I do understand we're very tight on schedule, but maybe there are some questions, one or two from the audience. It was very interesting. You have invited us to explore more. Yes, please go ahead.
Thank you for the talk. Maybe one question about these distillation steps. Is there any limit to them, and is there any information loss if we perform them?
So the lower bound is 1. We need to perform at least 1 diffusion step, and it depends on the technique. So usually we are able to go down to as little as 4 steps without any loss of quality. We can go even further and have fewer diffusion steps, but sometimes there can be like a quality loss.
Thank you.
Thank you very much. No questions on the slide, but there is... And there. Okay.
So the question, in fact, I'm not thinking about why do we need this distillation step. So I mean that why do we not train the, let's say, the teacher model with just 4 iterations or just 5 iterations? Why it doesn't work, in fact?
So basically, there is a lot of optimizations that have been done previously in the literature, and people have tried to reduce the number of steps of the teacher model, but there were some considerable quality reduction in that. So I think around 25 steps is the minimum, or 20 steps, depending on the use case. But the researchers have been able to reduce it only up to 20 diffusion steps.
Okay, I've heard there was the question there. Is it still valid? You want to still ask this question? Yes, thank you. This will be the last question. I do understand you have to transfer between the rooms. And I understand when you have interesting talk, you want to ask a question.
I would like to ask a question whether with distillation can we make it realistic to run those diffusion models on consumer level GPUs rather than server level GPUs, like, you know, running it on a maybe let's say high-end NVIDIA card, you know, like RTX 4080 or something like this.
So the only requirement is to feed the whole model into the GPU memory. So I think 4090 has like about 24 gigabytes of GPU memory. So I think it would be feasible to feed those models into consumer cards.
Thank you very much. Bravo. Thank you, Mateusz. It's a great talk and an honor to have you here.